Greetings and welcome to part 5 of the calculus series. In this video, we'll be solving coordinate geometry problems involving tangents and normals using calculus. We will also be rounding off this lesson with a real-world problem on how calculus is able to derive the focal points of a parabola that is needed for the design of satellite dishes. The success criteria for this lesson would be for students to be able to apply differentiation to solve coordinate geometry problems involving tangents and normals. In part 1, we started with the concept of the derivatives. For any given function at any given point, the derivative will tell us the gradient of the tangent at that point. We can also call it the gradient function. We have also learned that for power functions, the derivative of ax to the power of n is given by anx to the power of n minus 1. For this lesson, we also need to recall that the normal line is a line that is perpendicular to the tangent. An important relationship that we will need is that the gradient of the normal multiplied by the gradient of the tangent gives us -1. Aside from the power rule that applies to power functions, we have come across a few general rules. In part 1, we've covered the sum and difference rule. In part 2, we learned the chain rule. In part 3, we covered the product rule. And in the last part, part 4, we learned the quotient rule. Now, let's apply the rules to solve some coordinate geometry problems. Problem 1. The tangent to the hyperbola y equals to 2 over x at point P intersects the x and y axis at points A and B respectively. Find the area of triangle AOB. Pause the video here and give this question a good try. So first we can construct the hyperbola, and let's mark a random point on the hyperbola and draw a tangent to that point. So this tangent will intersect the x and y axis at A and B that we need to find. Next, we can also assume that this random point P has a x coordinate of A. The y coordinate will also be 2 over A. So let's mark that. So point P has a coordinate A, 2 over A. Now we can also find the gradient function of the hyperbola. So we'll differentiate y equals to 2 over x. And that will give us dy dx equals to -2 over x squared. So we'll substitute x equals to a, and this will give us the gradient of the tangent to be -2 over a squared. So now we can sub all this inside the equation y equals to mx plus c. So y equals to 2 over a, the gradient is -2 over a squared, the x is a, the c is unknown and we have to find it. So we can make c the subject. C will be 4 over a. This will tell us that point B is 0, 4 over a. Next, let's construct the equation of the tangent. Y equals to mx plus c. Now that we know the m and we know the c, the equation is y equals to -2 over a squared x plus c, 4 over a. Now to find point A, we will sub y equals to 0, and that will tell us that x is equals to 2a. Therefore, point A will be 2a, 0. Lastly, to find the area of the triangle, we'll just use half base times height. Amazingly, the a's will cancel out, and we'll get a final answer of 4 square units. Moving on to problem 2, which is taken from the O-levels. We have a quadratic equation y equals to -x squared plus 4x minus 6. The point P lies on the curve and has an x coordinate of 1. The tangent to the curve at P meets the x-axis at A and the y-axis at B. Part 1, find the area of triangle AOB. We are also given that point Q also lies on the curve. The normal to the curve at Q is parallel to the tangent to the curve at P. Find the coordinates of Q. Pause the video here and give this question a good try. So it's always good to sketch the quadratic graph out. then we'll label point P here, where the x coordinate is 1. We'll like to find the y coordinate as well, so we'll start x equals to 1 into the quadratic equation. That tells us the y value will be -3. Now let's construct the purple tangent to the point P, and that intersects the x and y axis at points A and B respectively. We'll find the gradient function that tells us the gradient of that purple tangent. So we'll differentiate the equation in y. That gives us dy dx equals to -2x plus 4. And we sub in an x value of 1. That tells us that the gradient of the purple tangent is 2. Now we can substitute the gradient and a point on the line to find the equation y equals to mx plus c. So we'll sub in y equals to -3, m equals to 2, x equals to 1 to find c. C will be -5. That tells us that point B, which is the y-intercept, is 0, -5. Now that we know the gradient and the y-intercept, we can find the equation of the purple tangent. So it will be y equals to 2x minus 5. If we substitute y equals to 0, that will tell us point A. The x will be 2.5. So point A is 2.5, 0. Next, we can find the area of the triangle AOB. We'll just take half base times height, and that will give us an area of 6 1/4 square units. And that's the end of part I. So in part II, we need the coordinates of Q, and Q is a special point on the curve where the normal is parallel to the tangent that we have found earlier. So the tangent at point Q is perpendicular to the normal as well as the tangent that we have found earlier as well. And since the tangent earlier has a gradient of 2, the tangent at Q must have the negative reciprocal, which is -half. So if we use the gradient function, the dy dx, which is -2x plus 4, we'll plug in the gradient of -half. So the x coordinate that gives us that gradient will be 2 1/4. So that will be the x coordinate at Q. We can sub the x value into the original quadratic equation. That will tell us the y value. Hence the coordinate of Q is 2 1/4, -2 1/16, and that's our final answer. Problem number 3. The curve y equals to 2 square root of 7 minus 3x passes through the point P, given with the coordinates k, 2 square root 7 minus 3k, where k is a constant less than 7/3. The tangent and normal to the curve meets the x-axis at t and n at the point -5, 0 respectively. So part I, find the value of k, and part 2, find the coordinate t. Pause the video here and give this question a good try. So let me first explain the broad strategy. We're going to find the gradients of Pn, the normal, and Pt, the tangent, in terms of k, and we're going to use the fact that the product of the two gradients is going to give us -1 because they are perpendicular. So first, let's work out the easy one. We'll find the gradient of the normal, and we can find this using the formula y2 minus y1 over x2 minus x1. This will give us the gradient of np. So it will be 2 square root of 7 minus 3k minus away 0 divided by k minus away -5. So the denominator can be simplified to k plus 5 here. Next, we'll work out the gradient of the tangent pt in terms of k. So to do that, we'll need to differentiate the curve. So we have the equation in y, but to differentiate this, we're going to use the chain rule. So first, we can substitute 7 minus 3x to be g. Now we're going to differentiate this. So dy dx will be the same as differentiating this with respect to g first. So take a d by dg of 2g to the power of half. And don't forget, we need to multiply by the chain, which is the dg dx. So we can differentiate 2g to the power of half. That will give us 1 over square root of g. And we can replace the g back with 7 minus 3x. And dg dx, when you differentiate 7 minus 3x, you are going to get -3. So times a chain of -3. So when we simplify that, the gradient of the normal is going to be -3 over 7 minus 3k. Now that we have found both gradients, we'll take their product, and that will give us -1 because they are perpendicular. The square root of 7 minus 3k can be cancelled from the numerator and denominator. This gives us -6 over k plus 5 equals to -1. We just have to make k the subject, and the answer will be k equals to 1. Now that we know that k equals to 1, we can substitute that into point P to see that that's just 1, 4. We can also substitute it to the gradient of the tangent PT, and that tells us that the gradient is -3 over 2. That means we can now find the equation of the tangent since we have a point and the gradient. So if we substitute the point and the gradient into the equation y equals to mx plus c, we'll get the equation of the line. So y is 4, m is -3 over 2, x is 1, plus a c. So we'll just need to find the value of the c. So making c the subject, c will be 11 over 2. Now we'll have the equation of the tangent. It'll be just y equals to m, which is -3 over 2x, plus the c of 11 over 2. To find the coordinate of point T, we'll just substitute y equals to 0, and that will tell us that the x is 11 over 3. That means the coordinate point T is 11 over 3, 0. And that's our final answer. So let's cap off this topic with a bonus question on the satellite dish. So we start off with a parabolic mirror. So I've drawn it in green here. And the idea is that it's given by the equation y equals to x squared. Although any quadratic equation, it would still work. I need to prove that any vertical light ray that lands on this parabolic mirror will be focused onto a point A. So what do I mean? So let's take a vertical light ray. It will bounce on this contact point shown in this yellow point, and we'll construct the normal to that point that looks like this. This will give us the angle of incidence shown in orange. And if you remember your physics, reflection tells you that the angle of reflection is equal to the angle of incidence. So the reflected ray will bounce off, and it will contact the y-axis at a point A. We want to show that this point A is a constant. So for every vertical light ray that lands on this parabola, it will always be focused onto this point A. So this point A lies on the y-axis, and we can give it a value 0, k, where k is going to be a positive constant that you have to determine. So if we think about the real-world application, if we have a satellite dish, what I'm asking you to find is where is this point where every ray will reflect to. So think about this, pause the video here, and give this question a good try. Since the point where the light ray was reflected lies on the mirror, we can assign it an arbitrary x value of a. That will give us a y value of a squared. That means this point here is a, a squared. Now we can construct a tangent to that point, shown here in purple. The gradient of that tangent will be given by the gradient function, the dy dx, which is 2x. And substituting x equals to a, the gradient must be 2a. This allows us to find the angle of incidence of the tangent. So shown here in this blue angle, the angle of incidence given by alpha is equals to arctangent of the gradient 2a. So first, I'm going to complete the right-angled triangle below by extending the vertical light ray. So now I have a right-angled triangle for the angle of inclination, and I'm going to mark its complementary angle here in red. This red angle has a vertically opposite pair marked here, and I can reflect its vertically opposite pair across the normal to get this other angle, which is also going to be equal. So these three red angles can be shown to be geometrically equal. And what is the value of this red angle? It is the complementary angle to the blue angle, so it's going to be pi over 2 minus alpha, all three red angles. Now I'm going to form another right-angled triangle by constructing this horizontal line and labeling this yellow angle here. And this yellow angle is very important because this will help us find the gradient of the reflected ray. So what can we do? Since we know it is complementary to double of the red angle, we can find the yellow angles in terms of alpha, and it will be 2 alpha minus pi over 2. So it's just 180 degrees minus away the 90 degrees minus 2 of the red angles. That's going to give us 2 alpha minus pi over 2. Now, by taking the tangent of the yellow angle, this will give me the gradient of the reflected ray. So let's call the gradient m. M is equals to tangent of 2 alpha minus pi over 2. And I can use the complementary angle formula here to simplify this. And this will give me negative 1 over tangent 2 alpha. So now I apply the double angle formula, and that will give me negative 1 minus tangent square alpha over 2 tangent alpha. So as we remember, the blue angle that we found earlier, alpha, is equals to arctangent of 2a. That means that 2a is equals to tangent alpha. So I can sub that away from my gradient. So the gradient will be simplified to negative 1 minus 4a squared over 4a. And this we can substitute into the equation y equals to mx plus c. So now that we know the m, we just need to sub in the y, the x, and we can find the c. And the c is the y-intercept, which is the coordinate for a, which is k. So what is y? Y is equals to a squared, x equals to a. And the interesting thing here is that if you try to simplify this equation, all the a's will cancel out, and you'll just get an outcome of k equals to 1/4. This tells you that no matter where your vertical line is, whether it's at x equals to 1, x equals to 2, every vertical line will bounce off the parabola and end at this point A at the point 0, 1/4. And I hope that you find this quite an interesting result about parabolas. So before we end this off, let's go back to the success criteria. Are you now able to apply differentiation to solve problems involving tangents and normals? So if you have any question on this topic, please post it in the comment section below. With that, we've come to the end of part 5. Do stay tuned to part 6, where we'll be looking at connected rates of change. Thank you for your kind attention and have a great day of learning.